Hi, my name is Michael. Today I'm talking to you about potential energy. So potential energy is the capacity for doing work based on position. In a system, as potential energy decreases, kinetic energy increases. As seen in the diagram here, we are holding a pie over someone's head. In this pie drop scenario, the pie is at its peak potential energy at this point. Once released, it slowly loses its potential energy as it moves down. As it is moving down, it loses its potential energy as shown by the equation here. As the height decreases, its potential energy automatically decreases as well. However, as it is decreasing in height, it is gaining in velocity, therefore the kinetic energy is increasing. And its peak kinetic energy will be right above the guy's head. Okay, so electric potential energy refers to the capacity for doing work in an electric field due to position. So the equation for that can be represented as electric potential energy equals the K constant times the two charges over the radius. So here in the diagram you can see that we have two positive charges that repel each other. In order to move the capital Q to point 2, it requires an external force that counteracts the electric field force. And then the electric field force is the force that would move large Q to point 1. And this can be represented by the equation of work external equals negative work electric field as they work in opposition to each other. Okay, so the quick example that we have for you guys is that we want you to find the work done by the electric field as big Q passes from R1 to point P. Please note that when you're doing this question that the change in potential energy equals the negative work done by the electric field. Okay, so to solve this problem, it helps to set up the potential energy at both points. So the initial point is 10 meters away from small q. So the potential energy equation is as follows. So U1 would equal K Q over R, or it would equal K 5 coulombs, 3 coulombs over 10 meters. And then the second potential energy, the final potential energy, would be U2, and that would be K times 5 coulombs times 3 coulombs divided by 20. And then to simultaneously solve these, we want to plug them into delta U, the change in potential energy. So I'm going to go over here, and I'm going to get delta U equals U2 minus U1. So if you plug in all the numbers where K is 9 e to the 9, you should get as follows. U2 will be 6.75 times 10 to the 9 joules, and U1 will be 1.35 times 10 to the 10 joules, which will give you negative 6.75 times 10 to the 9 joules. And this will give you change in potential energy. However, as we know, change in potential energy equals negative work done by the electric field. So therefore, the final answer should be 6.75 times 10 to the 9 joules for work done by the electric field. The next problem involves finding the potential energy in a system containing 4 identical charges of 3 nanocoulombs each. The solution is as follows. So how we set it up was we applied the potential energy that each one has on each other. So there's potential energy that 1 has on 3 and 3 has on 1. So we wrote it here. So we have the potential energy of 1 on 3, 1 on 2, 1 on 4. And then we have the potential energy of 3 on 2, 4 on 2, and 4 on 3. So that sets up all the electric potential energies that are acting in the system. Now to figure out the distance between 1 and 4, we had to set up the distance equation. And the answer we got for that was 5 meters, because 4 squared plus 3 squared equals 25, and the root of 25 is 5. And then find the angle. We got 37 degrees, and we set up the reverse sine or the reverse tan of our distances, and that gave us 37 degrees. And then plugging all this into the potential energy equation of K equals U equals K Q1 Q2 over R, we got all these values. So I'll go over certain ones because it would take too long to go over all of them. So for the potential energy of 3 on 1, how we set it up was K is 9e to the 9 times the two charges, which are 3 nanocoulombs each, so we put squared. The 3 nanocoulombs were converted to coulombs, so 3e to the negative 9, and then divided by the distance in between, which is 3 meters. So this will give us 2.7 e to the negative 8, so 10 times 10 to the negative 8, J joules. So this means that it's electric potential in the y direction. And then for the potential energy of 4 on 1, or 1 on 4, it's the same thing. We got a total value, because it's across the distance here, of 1.62 e to the negative 8 joules, by plugging in 5 as the distance instead of 3. However, there are components to this energy. So to find the components of the energy, we multiplied 1.62 e to the negative 8 joules by cos 37 and sine 37 to get both the I and J components of the force, of the energy. And then the same can be said for these ones as well. The values each match with one of them. So U31 matches with U42, and then U21 matches with U43, and U41 matches with U32, just based on how they are in our diagram. And then when you add all the components together, you get our total electric potential energy being 6.64 e to the negative 8I plus 7.35 e to the negative 8J